Hi, this is the second lecture on the dual active bridge converter. In the first lecture we saw the basics of the converter. Uh, this converter is useful when bidirectional power flow is required, and for example in an automotive system where you might want to connect the 12 volt DC bus with a 42 volt DC bus, or in an electric vehicle between the 12 volt DC bus and a higher voltage DC bus, probably in the hundreds of volts. It's also useful for providing galvanic isolation between DC buses, where you want to minimize the size of the transformer. Also, for example, on a Navy ship, if you want to isolate two different zones on the ship which have DC power systems, then you could use this kind of converter. Another application is interfacing energy storage to the grid. So wherever you have a need to interface energy storage, you need bidirectional power flow, and you typically want isolation. If there is a need for reducing size also, then this converter is ideally suited to that application. So we looked at how the topology can be derived from the simple case of the two-bus AC system. We went through the current waveforms, the soft switching details. We said the current has to be lagging to provide soft switching. We looked at how the power transfer can be derived, and that the power transfer is in the converter is very close to what you would get in the two-bus AC case. And we looked at how you could realize the inductance L as part of the transformer. In this lecture we're going to talk about the converter design details. The first design parameter is the transformer turns ratio. To maximize the zero voltage switching range at nominal conditions, we choose the turns ratio to be equal to the ratio of the voltages on the respective sides. So this follows from the current equations here. So if you choose NP over NS equal to VDC1 or VDC2, then M is equal to 1, and these two equations then just reduce to product of phi with this constant I base divided. So what that means is, to get zero voltage switching, we want IL0 to be greater than 0 and IL1 to be greater than 0, which translates directly to phi greater than 0. So as long as phi is greater than 0, we'll get zero voltage switching, which means we'll get zero voltage switching down to zero load. So theoretically, with this choice of turns ratio, we'll get zero voltage switching down to zero load. Switching frequency is arrived at after a more complex trade-off. It has more factors you need to consider. First of all, based on the power and voltage level, we would determine what kind of switch we're going to use, and also the magnetic material. If the voltage level is below 500 or 600 even, we could use MOSFETs. If it's higher, then we would typically use IGBTs. And then that choice would also place a limitation on the switching frequency. The magnetic material would typically be ferrite if you're operating below approximately 10 kilowatt and you're operating in the tens of kilohertz. If you have higher power level, then you would typically use tape wound cores, probably something with nanocrystalline material. And the trade-off here is between the heatsink size, the transformer size and weight, and the efficiency target for a given thermal solution. So the heatsink and the transformer size and weight will depend significantly on how you actually cool your system. The switching frequency will also depend on considerations of switching loss at light load, because at light load we are not going to get zero voltage switching, so high switching frequency will mean higher switching loss, and that would be a significant percentage of the total loss at light loads. The controlled bandwidth is also determined to some extent by the switching frequency. So because we'll be using average dynamics of the system, will typically limit the control bandwidth to approximately 1/3 of the switching frequency. The implementation of the control can also be tied to the switching frequency. So if you have a digital implementation, then typically your control loop sample time will be equal to the switching time period or half the switching time period. And that will the sample time will then add its own sample and hold delays to the control loop. So you have to consider the control loop also when you are deciding switching frequency. The inductance value is the most important design parameter, and we'll talk more in detail about this. We also need to look at magnetizing inductance of the transformer, and like in any other converter, we need to determine the capacitor size on the input and output to make sure the input and output voltage ripples are within the requirements. I just listed some of the design equations. Maximum power transfer, which you can derive from the power transfer equation you saw earlier, the RMS current in the primary and secondary, again you can derive these from the waveforms. These are useful to compute the conduction loss in the switches and the transformer windings. You can also compute the transformer magnetizing volt seconds, which will determine the transformer size primarily. And using the inductor current waveform, we can also determine the capacitor ripple current waveform and compute the charge requirements. Now we said that if we choose the turns ratio of the transformer equal to the nominal voltages on either side of the transformer, then we get soft switching down to zero load. But that's only when the input and output voltages are at their nominal values. If they are not equal to the nominal values, which is typically the case in any power converter, then this variable m is not equal to 1, and we do not get soft switching down to zero load. So for example, if the output voltage is less than the input voltage, then m is less than 1, and then IL0 greater than 0 is guaranteed if phi is greater than 1 minus 1 over m. Because m is less than 1, this quantity is negative, so as long as phi is greater than 0, then we get soft switching. So for power transfer from left to right, we're going to get soft switching. For HB2, however, the secondary side bridge, m is less than 1 and there is a positive value of phi below which we're going to start getting hard switching. uh, these are quantified here in terms of the power transfer level in this graph. Ignore this red curve for now. So it's the blue curve that we should be concentrating on. So for m less than 1, we get hard switching on the secondary side bridge below some power transfer level. For m greater than 1, we get hard switching on the primary side bridge below some power transfer level. Above this blue curve, we get a soft switching for both the bridges. Now these conditions just guarantee that the inductor current is greater than 0. It does not actually account for the capacitance present at the switching node. When we account for the total capacitance that is present at the switching node, then we need to make sure that these currents are high enough to discharge the capacitance in the programmed dead time. So what that means is now instead of this being greater than 0, these currents being greater than 0, they have to be greater than some threshold value, and the effect of that is in reality we get soft switching down to not this blue curve but this red curve, which is somewhat above the blue curve. The dead time that we program also determines how effective the soft switching is. So you could make the dead time programmable with the current. This is typically done for the phase modulated full bridge converter, and the same principle can be applied here. So as the inductor currents IL0 and IL1 are getting smaller and smaller, you can start increasing the dead time. As they keep increasing, you can start decreasing the dead time, because you know that for when the current is higher, the capacitance will be discharged faster. The current is smaller, it will take a longer time to discharge the capacitances. I'm not going through the equations relating to the transitions, including the capacitances at the switch node. They are included in the appendix to these slides. I recommend that you go through these. These are required for doing a preliminary design of the converter. Okay, we said that the inductance value is the most important design parameter. Here are some general considerations for determining the inductance value. Lower inductance value will lead to a higher power transfer capability and also a smaller phase shift range that you have to work with in the converter. If you keep increasing the inductance, then you'll finally not be able to transfer enough power through the converter. So there's a maximum value of inductance for given values of input, output, and the maximum power transfer you want to have in the converter. You can come up with a minimum value of the inductance also using this equation. This is not very useful. It may be somewhat useful if you have a resolution on the minimum value of the phase shift. For example, if you have a digital realization and phi has some resolution in terms of number of bits you're using to realize the control. So if your resolution is very low, if your resolution is very coarse, then having a small value of inductance will mean that you cannot control the power transfer to a very fine degree. So you want to limit the the minimum value of your inductance in that case. Lower inductance typically will reduce the size of the inductor, and therefore it will be easy to integrate it with a transformer. Lower inductance will also typically lead to a smaller capacitance requirement and lower RMS current in the capacitor and lower RMS current in the transformer and the switches. Higher inductance will enable a wider ZVS range, so we'll be able to achieve ZVS down to a lower power level, and this is particularly important if you're operating away from the nominal input voltage or nominal output voltage. Starting point for optimization is an per unit impedance for the inductance of approximately 0.25 to 0.5 per unit. The base here is defined as or defined with the power base being equal to the rated power and the voltage base being equal to the input DC voltage VDC1, and this inductance then is also referred to the primary side of the transformer. So we saw that there are considerations to choosing the value of L. Reducing L will typically reduce conduction loss in the converter, but increasing L will result in reducing switching loss, particularly at low loads with wide variation in the input and or output voltage. So so in a real design, what you do is a numerical trade-off between these aspects: the conduction loss, switching loss, and the size of the inductor, transformer and capacitance, and come up with a value of L that minimizes the total loss and the total size. These are the typical curves that kinds of curves that you get when you're doing the optimization. These are for a 10 kilowatt design where both the input and output voltages are 700 volt DC. So in this curve you can see that by increasing L we are able to achieve ZVS to lower and lower power transfers. In this curve you can see that increasing the value of L is resulting in increased RMS current for the FET and also increased average current for the FET. Here you can see the capacitance requirement, and the RMS current in the capacitance is also going up with the inductance value. By the way, just as a point of reference, for this design I ended up choosing L of 100 microhenry as a compromise between the ZVS range, the conduction loss, and the size of the different components. So typically the leakage inductance is sufficient to give us soft switching at high load, but not able to provide soft switching at light load. To increase the ZVS range to lower power levels, it is better to utilize the magnetizing inductance of the transformer. This does not translate to a higher RMS current, significantly higher RMS current, as you would have if you were trying to achieve ZVS just with the leakage inductance. And it acts in complement to the leakage inductance. So what happens is at low loads the phase shift is small and the magnetizing current is also small. As you increase the phase shift for high load, the magnetizing current value goes down. So at high load magnetizing current is lower and you're relying more on the leakage inductance. At light load the leakage inductance is not able to help you, but you have higher magnetizing current, so you get the benefits of both magnetizing current and leakage inductance. There is a downside to including the magnetizing inductance. It has a penalty in the maximum power transfer capability of the converter. You can derive this if you rewrite the equations incorporating the magnetizing inductance, rewrite the current equations with the magnetizing inductance also. This factor K2 is given by this expression here, and in this expression this variable K is the ratio of the magnetizing inductance to the leakage inductance. This is not a real problem from a design point of view, because the rated power is typically less than the maximum power transfer capability you have in the converter, and also typically you would have factor of 10 for this K. So K will, if K is 10, then you can see that K2 is just 1 over 1.025, so you're not compromising the capability by a big amount. A factor of 10 between the magnetizing and leakage inductance is a good starting point for design, and again the best thing to do is optimize the design numerically, either by simulating the circuit or by computing the different loss components. Now for the transformer design, what we need to start are the RMS currents in the windings, the worst case flux in each part of the magnetic structure, and this will vary with the load. So at high loads you'll have high flux in the leakage path. At zero load you'll have maximum flux for the magnetizing part of the core. Then we can choose the core areas, starting with some assumption for the operating flux density. Typically you would use something in the range of 0.15 to 0.25 Tesla for 3F3 type ferrite, and something like 0.25 or up to maybe 0.4 Tesla for nanocrystalline tape-on cores. Then you go through a design iteration for the transformer, compute the loss in the windings and the core, and see if the loss is meeting your target efficiency and thermal constraints, whether or not you're able to keep the core temperature down to the operating limit of the magnetic material. The ripple current in the capacitor can be computed from the input and output inductor current waveforms, or the bridge output current waveforms. A starting point can be when you don't have any magnetizing inductance, and you can use that to come up with capacitance required to meet the ripple specification. Finally, you should confirm your efficiency in ripple by simulating the entire circuit with known values of the switch resistance, switch capacitance, transformer parameters as designed, and some estimate for the transformer intra-winding capacitances also. Now we we just looked at what is essentially the power component design for the converter. The other aspect of the converter design is the control design. So for example, we might have a situation where VDC1 is a voltage source and VDC2 is actually a resistive load, and we need to regulate the voltage on this side on VDC2. So to do that, we know that our phase shift phi is the control variable, and that's what we apply to this converter. Now we need a dynamic model for the converter from the phase shift phi to the output voltage, and based on that model we can then go ahead and design a suitable compensator for the system. So the dynamic model for this particular example is straightforward, and here we'll be concerned with dynamics averaged over one switching time period. That's what this bar over the variable indicates. So the capacitor voltage dynamics are then given by this equation. It's quite straightforward, following from the circuit here. The important thing is the H bridge current output IHB2, and this is computed directly from the power transfer. So this is just the power transfer divided by the output voltage. And we have the same parabolic relation now between phi and IHB2, the output current of the converter. So if you're doing a linear design, we can go ahead and linearize this at an operating condition. So at an operating uppercase phi, this is the gain of the converter, VDC1 or XL times 1 minus 2 uppercase phi divided by pi. And the thing to note here is that this is static gain, so we don't have any dynamics in the converter if we assume that the converter is responding in one switching cycle. This is a first order model, and more complicated models are available in published literature. I've included one reference which talks about a more accurate model, more accurate dynamic model for the converter. So now going back to our control loop, we know this current gain, which is a static gain from phi to IHB2, and this is what's feeding to the load. This is just a simple first order RC system which gives you the output voltage, compare with the reference, and then you design a suitable compensator to get the dynamic response you want and stabilize the system. In conclusion, this is an example of a dual active bridge prototype. It's a 25 kilowatt design. Input and output voltages are 700 volts with a plus minus 20% variation expected. The switching frequency is 25 kilohertz. The two identical H bridges, one over here, one over here. The gate drive and power supplies for the bridges are on top of the board. The switching devices, which are silicon carbide MOSFET modules, are under the board, mounted on the heatsink. The capacitances on either side of the bridge are these film capacitors on top of the board. This is the transformer. It's made with nanocrystalline core. It has a high leakage, also realized inside the transformer via a separate path for the flux, for the leakage flux. This is the control board for the system. These are some operating waveforms, the primary and secondary voltages, and in the lower part the primary and secondary currents. Primary and secondary currents are a little bit different because of the magnetizing current. Here are the measured efficiency numbers. The target efficiency for this converter was 98.5. We are able to get close to that, probably 98.4 at the 10 kilowatt level with silicon carbide, which was significantly better than the silicon IGBT version of this converter. We got a reduction of losses by a factor of approximately 3, and a simultaneous reduction in the size and weight of the converter also by a factor of 3, by going from silicon IGBTs to silicon carbide MOSFETs. That's just an aside to our main discussion for the dual active bridge. So that concludes the lecture on the design of the dual active bridge converter. In the next lecture, we're going to look at some of the variations of the dual active bridge converter, PWM control, and some small topology variations. Thank you.